Good afternoon again, ladies and gentlemen. Certainly the fullest room that I've ever seen for an afternoon keynote, which would normally be snooze time. But of course, that is a tribute to our speaker from Bosch Software Innovations, the legendary, I want to say, because did not Richard Soley give him a good advanced promotion in his keynote this morning, the legendary Dirk Slama. He's going to expound on best practices, and it involves a drill, a demo, a little gizmo. I'm just going to get off and admire. Dirk, please, entertain us.
Good afternoon. I'm actually not going to dance for you after this. I'll try to stick to the topic. Best practices for IoT deployment. And I have one best practice for you to start with. Don't believe the hype. So what I would like to do is, I would like to look at a couple of very concrete examples I brought with me, some demos I would like to share with you, and then also, actually, I would like to look a little bit into the future and see where all of this hype is coming from. Actually, when I was in Hanover earlier this year at the Hanover Fair, I had one moment where I thought, okay, I understand now a little bit better where this hype is coming from. This is pretty cool, isn't it? A robot turned into a thingy that you know? Of course, there's no lack of ideas, right? I mean, I'm assuming that you've attended a lot of presentations today where many different people shared with you their vision for the industrial IoT. So many different ideas. I mean, if you just look at, for example, the potential in drones, right? So Amazon made a big push last year announcing that they would use drones to deliver parcels. Might be some time before this happens in New York, but actually German postal service DHL launched the first commercial postal service to the island of Used to deliver parcels to this island so that the poor guy doesn't have to row over there once a week. I don't know if we will ever see the intelligent toast oven. So many ideas from 3D printing to actually what you see here, solar roadways. I really like this. The idea basically that you have intelligent pavement. Okay, so imagine you have a road going into the city that's crammed every morning. You could basically use this to make it, let's say, 3 roads into the city and 1 road outwards in the morning, and then at lunchtime just switch this over to basically get the traffic out of the city using this intelligent pavement. And of course, for the friends of the A-class, it can also basically sense if an elk is crossing the road and then illuminate it from the bottom, okay? There's, of course, from a Bosch perspective, so I work for Bosch Software Innovations. We basically help Bosch customers and Bosch business units to enable IoT business models. There's, again, no lack of ideas, right? So if you look at just the connected vehicle alone, from parking services to autonomous driving, etc., or take this little guy up there, the IoT-enabled lawn mower, or other things like heating technology. I don't know, for 10 years we've been talking about the intelligent refrigerator that tells me when the milk goes sour. I still don't see this coming. And frankly, another thing that I didn't see coming when I started about 5 years ago was the intelligent tightening tool or power tool. And on this one, I actually was dead wrong, and I'll tell you why in a second. Just a brief discussion on what our understanding of industrial internet is, because it seems like there's many different ways of looking at this. So we really look, I mean, you know, Bosch, German company with a proud heritage. We look at manufacturing on the one side, so Industry 4.0, but then around manufacturing, we have lots of topics like supply chain, energy, smart building, up to health and mobility, etc. So what I would like to do here is, on this industrial internet event, focus on a couple of more industrial use cases and then see what kind of best practices we can derive from this. Let's start by looking at engineering. Okay, so let's take one example, car component engineering. We have done a project, or we're still working on it, where we basically now are able to collect real life data from vehicles which are deployed in the field, so normal commercial vehicles, okay, and basically use IoT technology to tap into the data that's coming from these cars. For example, car brakes, power steering, pumps, battery, etc. And we can get very large amounts of data from vehicles driving in very different conditions, urban environments, countryside, etc., that are very, very difficult to simulate. Okay? And this is a unique chance for us as a car component manufacturer to actually use this data to learn about how our products are actually performing in the field, and then use this information to basically optimize our engineering process. So this is now live out there. We've deployed this for 4 large OEMs. I would say about 1.2 million cars out there now that deliver this type of data to us, and that's, of course, manna for engineers. The next example, smart heating, okay? This is an example for actually an industrial heating system, which is manufactured and sold by Bosch. And we have built a solution around this that basically allows us to do remote monitoring of heating systems, both for private households as well as for commercial systems. Again, a very similar architecture. So we are deploying our asset management software close, or actually on top of the asset, where we basically integrate with different sensors that give us data, for example, about the physical conditions of the asset, etc. And also to manage the remote connectivity to the backend, where we basically have a stream processing component that can digest the incoming data from many thousands of such heating systems, and then basically manage the data, and also deploy advanced machine learning type of algorithms to learn about this. So it really starts in terms of the applications with just listing the registered appliances and get their status. So that's very helpful for the field service people. And then also get real-time information about how they perform. And in case of a problem, not only get a deep analysis of the problem based on the sensor data, but also in terms of prescriptive maintenance, get first recommendations how you can actually go about solving this problem. So I think this is another great example. Let's move on to something which is actually close to my heart. We just bought a house 2 years ago, and I've become an avid DIY fan, and I just love it that Bosch Power Tools has so many cool tools. Now, yeah, well, they wouldn't, I guess, see me as their prime customer, but still. If you look at the products they are building for our commercial customers in the construction business, this is also going towards the IoT. So I brought with me here a jackhammer, and don't worry, I'm not going to do a performance with this right now. One challenge that you have if you are running a construction company and you have maybe, I don't know, 50 or 100 people using hundreds of these tools and being on site at different construction sites every day, is how do you actually make sure that the right people are bringing the right tools with them to the right site, okay? And how do you also make sure that the tools are not getting misplaced, okay? So in order to solve this problem, what we built is a solution that is leveraging a small tag, which is actually Bluetooth low energy enabled, okay? And we can attach this tag to these kind of tools. You actually see here, there it is, right? For the next generation of tools that we are selling, we will actually also have this built in, okay? And one thought that our product management had on this was that you cannot always assume that at every construction site you can build up a dedicated network to manage these tools. So on the other hand, you can actually assume that about 80% of construction workers nowadays have a smartphone with them. Okay? So what we've built is a smartphone app that can basically connect to these tags which are attached to the tools. And that basically means that we can then track the tools, okay? See where they're used, etc. And actually starting way earlier. So the tool that we're offering is called Track My Tools. It starts in the morning when you need to get organized. You're loading up your truck. You have to make sure that you're taking the right tools with you, etc. Okay? We can use the application to make sure that all the right tools are actually in the van, etc. When we arrive at the site, we can also do a checkpoint. And then when we leave the site, we can make sure that all the tools are being brought back. Okay? And all of this basically leveraging existing infrastructure. So I would say that's a pretty good case for IoT used in the construction business. Let me also give you another example, more from the industrial side. So what I was showing you earlier on, the jackhammer, that's not something that, of course, you want to see used on an aircraft, right? However, a lot of mobile and handheld tools are being used in car manufacturing, aircraft manufacturing, etc. But the rules that apply to the use of these tools are slightly different, okay? What we see is that quality control, for example, is a key concern, right? So there's two reasons. First of all, the reliability and security of the final product. So you want to make sure that there's no faulty connection anywhere, right? If you take a medium-sized commercial aircraft, it has about 400,000 joints, and every single of them has to be perfect, right? A second reason is the earlier you can actually get involved in detecting potential problems, the less costly it is to actually deal with these problems, right? So if you basically find out, for example, you're performing a tightening process and the screw breaks while doing this, and you notice immediately and you can fix the problem, it's way cheaper than actually do this many steps later in the assembly process. So we've teamed up with Tech Mahindra and Cisco to set up actually the first public testbed that was launched by the Industrial Internet Consortium, IIC. Most of you saw Richard Sorley this morning talking about the IIC. And for us, that's a very nice complement to the perspectives of Industry 4.0, of course. In this testbed, we basically started to develop this kind of advanced fleet management for industrial power tools. And what I would like to do actually is to show you a short demo of this. I don't know. We tried this early on. Perfect. Okay, so what you see here, we just switched to my laptop here. I converted my laptop into a local area network. And what I brought with me here is another tool, this time not from our Power Tools division, but from our industrial division, Rexroth. Okay, and this is a very different type of tool. Okay, this is actually highly intelligent. It has on top of it, you can see this here, a real-time processing unit that can interface with the tool. We have deployed sensors on the tool that give us a lot of data about the tightening process, and it is Wi-Fi enabled to give us actually information about the tightening performance. So let me just log in here. And see if that works. Okay, so this is now basically directly remotely communicating with these tools. So let's go to analysis. I'm sorry, I used the German language profile. Let's not bother changing it. So here, for example, I can see the as-is data received from the tool, okay? And here I should be able to see the current curve. Okay, so what's relevant is that I am basically trying to get the torque and angle per tightening process. Okay, so let's imagine I am now performing a tightening process on an aircraft part or something like this. Okay, press the button, I have pre-selected the program, and a couple of seconds later, you should see, okay, yeah, you just saw how it changed. So this is now real live data from this tool, okay, uploaded to the backend system. And that's very valuable data, okay, because that can be proof whether a particular tightening process step was right or actually went wrong, okay. So if we just go back to the PowerPoint presentation, thank you. What we've built on top of this functionality are, for example, dashboards that give us insight into operational equipment efficiency, defect rates, etc. Okay, and also more traditional fleet management type of KPIs, tool availability, tool utilization, etc. Okay, and on top of this, we have now created a database. Okay, and this is actually one of these examples where it is actually a big database. Not only in terms of the volume, in terms of ingest, but also in terms of velocity and all the other aspects of big data. This is something that we're using now to help customers create a recording of every single tightening process they perform. Okay, so if you take a large OEM in one factory, that will be millions of tightening processes per year. And then specifically for each type of material, for each type of drilling technology we're using, for each type of screw, for different types of coating which are applied to different types of screws, we are creating a tightening profile, okay, that builds up over time. And this tightening profile we can then use to match this against the as-is data which is captured from this tool, okay? And that immediately basically can be used to trigger an alarm if there is a deviation between the as-is tightening performance and the data we're getting from the database. Another thing that's keeping us quite busy, early on when I was talking about the technology we're using on construction sites, okay, here in the industrial environment we have some different requirements. One of them is precision. For example, we want to be able to identify which tool is used at which work cell. Okay, because I mean you all know the horror stories of people forgetting tools inside of ready-made products. Okay, and especially in car manufacturing and aviation, that's a no-go. Okay, so we want to be able to track different types of tools, and we're using indoor localization to do this. One of the still not fully solved challenges of this is that we actually want to get much better precision in terms of indoor localization at a, well, as low as possible price tag. So this is something where I think we have a reasonable interim solution, but where we continue to work with partners to basically get the best possible precision at the lowest price tag. And one reason why we want to do this is because this initial use case that only looks at basically associating tools with a work cell, we think can be refined. So in a phase 2 of this test bed, which is not yet commercially available as opposed to the phase 1, we are really looking at cyber physical systems where we basically want to get the data from the 3D PLM systems, okay, which has all of the bill of material information in them, and combine this with indoor localization data so that we can track the precise position of the parts we're working on, okay? And basically use this information and combine it with the precise information of which tool we're using so that we can basically identify, for example, which joint are we working on using what type of tool, so that we can then basically go back to the 3D PLM system, get the work instructions, and basically activate the right program on this tool, for example. Okay? Because, as I said earlier on, depending on material, type of joint, etc., we need to use different types of programs. And then also to basically be able to create a quality lot from the type of data we saw earlier on, and take this quality lot from the tool and associate it back with the data in the 3D PLM system, so that in the bill of material for each security relevant joint, we basically have proof that this operation was performed according to spec. Okay? And that is something which we think maybe still 1 or 2 years away from this in terms of delivering the solution. But the potential of this is extremely high, not only for quality management purposes, but also really from a production optimization point of view. Because as I said earlier on, the earlier I can detect any type of problems, I can go to my backend systems, the MES, the MOM, etc., and get information about how to deal with this specific problem without having to stop the entire assembly process of, for example, an entire aircraft. Okay, so this is very powerful and very important. This is an example. Actually, this is something that we were shown in exactly this room here a couple of months earlier on. So you see here, we have a 3-dimensional model of this hall that we're sitting in. Okay, the little red dot in the lower right corner, this is actually the position of the tool as we had it at the time. You see the 3-dimensional model of a car engine that we're working on, the model of the tool, and even an avatar that we were able to track using sensors to basically make this vision come true. So I would say that's a really good first step towards this, whatever you want to call it, cyber-physical system or digital twin type of approach. And as I said, this is something in this area where we're focusing on more on the medium term. Of course, another thing we're focusing on here is additional tools. So tightening, yes, it's very important, but also welding, riveting, and so on. And also, Richard, I think, has mentioned this morning. It is absolutely mandatory that we're creating a solution here which is open. I mean, of course, we love to sell you our power tools. In particular, our power tools people do this. But when I'm talking to manufacturing customers, they're telling me that, well, they do have tools from many different vendors, okay? And in order to make this work, we need to create interfaces that are open and that can be used to plug in multiple different types of tools for these kind of solutions. So one of the things on the technology side that we see is extremely useful here is Vorto to define the interfaces, and then, for example, OSGI to manage the back end of that. So just as an outlook here. One interesting question, of course, is what can I learn from all of these different case studies? That, of course, is a question we can't answer to the full in a 30-minute presentation. But because we're getting this question a lot, we started to look at how can we actually provide a more formalized way of building IoT solutions. And that's one of the approaches that we found. We looked at many different use cases, so those that I was just talking about, and other extremes like the Large Hadron Collider at CERN, which is using 1.2 million sensors to basically create a digital model of what happens after a particle collision at near light speed. Just to give you an idea of the types of solutions we analyzed. And what we identified is, what's very common is that in the real world, you have an idea, but it's unproven. So Einstein, he had an idea, right, which eventually led to this theory about the Higgs boson, right? The next thing is that you create a digital model, and you say, okay, if I had this model, then I could validate my real world idea against this, right? And a couple of questions you have to answer for this is, for example, what is the granularity which is required for your digital model? So in this example, this is actually based on soccer, right? So one question is, for the solution I want to build for my theory, is it sufficient if I have a database that tells me the final score of all of the games, right? Or do I need to know, for example, at what time each goal was scored? Or do I need to also find out who scored the goal? Or do I want to go to such an extreme where I'm actually creating a heat map that shows me the precise movement of every player as he moves on the field? Okay, so that's, in our experience, a first thing, the creation of this digital model. And you have to be very careful here because, of course, the more fine-grained your digital model, the more costly, most likely, your solution will be in the end, right? Then the next thing you have to look at is what are the possible inception points? Okay, so if I'm taking this simple soccer analogy, how do you actually find out if there was a goal scored in favor of your club? So we're in Berlin here, Hertha BSC. I would assume if we score a goal, then there is like big applaud, and if we get a goal, then there will be a loud boo, right? So maybe I can just deploy basically some microphone in the stadium as a sensor to get this information. Or if that's not sufficient, then I might have to think about deploying a more advanced solution, for example, using goal scoring technology, as it was actually used for the first time in this World Championship in a game, I think, between France and a Latin American football team. But if you can't actually, if you're not part of the FIFA, right, and they won't let you do this, then you maybe have to start being creative about these inception points, right? Just let me give you another example. We've built a system called the eCall system, right? And maybe it's a little bit typical Bosch, because the idea is that we deploy a sensor in a car, right? And then the sensor tells us if there was an accident. So the Bosch engineers, of course, said, yeah, great, we deploy an acceleration sensor, and we also hook into the CAN bus to get data from the airbag. Okay, so, and we did this, and it works great. But the point is, these are two fairly expensive inception points, because they mean that you have to do a retrofit in the car, and you have to install a communication infrastructure. We saw another example earlier on for using a mobile phone as an inception point. So maybe this would actually have been sufficient in this eCall example, right? So again, it's a question of cost versus precision. Once you have this, the next thing is the reconstruction of your digital model. So what type of, for example, sensor data fusion algorithms do you have to deploy to really create the digital model that you need out of the analog data, right? Take autonomous driving, where I have LiDAR, radar, video cameras, ultra-short wave sensors. And out of all of this information, I want a digital model that tells me there's a little child 200 meters ahead of you, standing very close to the sidewalk. Better slow down. Okay? So that's the reconstruction process. So this is one example for how we think you can start thinking a little bit more structured about best practices for the IoT. What we did is we analyzed about 34 different detailed case studies. So you can see here the Large Hadron Collider, the Bosch eCall solution, and so on. And we tried to extract best practices from all of these different solutions, and we documented this in a book. It's actually all online, enterprise-iot.org. We included many different end users and vendors in this, and it's a constantly evolving effort. We're working very closely with the ISC, for example, to make these best practices part of the offering of the ISC to the market, and also from our perspective, from Bosch Software Innovations perspective, we really see the need to support our customers from business model design to definition, for example, of what is the minimal viable product of your solution, to solution development, and then, of course, operations. So That's, I think, very important in terms of capturing these practices and making them accessible to a broader audience. So we are investing quite a significant amount of resources in this. If you want more information, go to our website or talk to us. We're happy to share this with you. I would say that was a 30-minute rundown on use cases and deriving best practices for them. And I would like to actually thank you for your attention. Thank you very much.